Okay, welcome back to System and MiniConf. Next up, we have Paul Warren talking about some slightly more advanced networking with Linux. A reminder, if you have questions during this talk, just put them into the questions tab in Vinulus. Okay, take it away, Paul.
Alrighty, g'day folks. Yeah, my name's Paul, here to talk about some stuff I've learned over the last little while networking with Linux. First of all, a bit of a warning that I'm not a network engineer. There are bits that I don't know, and there's probably gaps that will, potentially cause issues. So don't blame me if your network stops working, and maybe don't go try building an ISP based off this talk. And as another sort of aside, I've just moved house, and that was an experience that I was woefully unprepared for. So please keep that in mind. So I thought we'd start like, what even is a network? I mean, is it Ethernet? Maybe token ring, IPX, AX25, or is it something more like IPv4 or 6 or TCP? I like to think of it as something that allows connections between computers. In this talk, I'm mostly going to talk about Ethernet and IPv6, although it's sort of doesn't really matter that part of it. And the stuff we'll talk about will be mostly based on Ethernet and IP. Most of us probably work in a managed network where the idea is to control connections between computers rather than just allow. They also scale much more. Managed networks also scale connections between computers. And you've probably seen this diagram of the three-tier core distribution access network there, which is not likely to be something we have at home. We have a pretty flat edge network at home. But this diagram, while it's nice, it does hide a lot of complexities at each layer and is not something I know a great deal about. And I invite you to research further about this methodology. Networking, as you probably have already understood, is about layers, like an onion or a parfait, if you like that better. There's that 7-layer thing from the OSI, which I can't remember what it stands for, which we can mostly ignore because it doesn't, because what we generally use in the real world doesn't sort of conform to it very well. But it is a good framework for assisting in understanding. So, the general networks we use are basically Ethernet with IP on top of that, and then various flavors of other, layer 3 networks of ICMP, TCP, and UDP. It can also be administrative overlays, things like firewalls, web proxies, SSL, man-in-the-middle things for enterprise, but also things like access rights and bandwidth shaping and things like that. There, no, that's the wrong button. Sorry about that. Yes, and the last one there was for VPNs and tunnels, which allow you to put networks through other networks and have them appear in strange places. And that that means that the physical layers don't have to match the logical connections, and you can distribute your network across multiple physical networks, and it all should just work. They're also a bit fractal in nature, so large-scale networks are sort of self-similar the more you delve into the details. But we can ignore a lot of this complexity for the stuff that I'm going to talk about today, because that's really advanced networking, not slightly advanced networking. So I sort of start off with an easy one on Linux, which is VLANs, or virtual local area networks. It's an Ethernet layer protocol designed to limit broadcast storms, and you can use it to separate IP networks on the same Ethernet. There is a concept of a tag in this in VLANs, which is a 4096 goes up to 4096, so some bit number that I can't remember, that is used to separate these VLANs at the Ethernet layer. It's part of the Ethernet frame. The untagged network is the default one that your NIC will respond to if nothing else is set, and then most NICs need to have some magic done to them so they can respond to tagged packets from the Ethernet. It's defined in the IEEE 802.1q standard, and it's a pretty interesting read. In Linux, it's pretty easy to get one going, and with the IP command, you just run something like that. You add a link, give it a name, and tell it that it's for VLAN ID and then your number. Then you can, as normal, add addresses, routes, and whatever on top of that, and then set it up to make it all go. Distributions do this in various different ways. In Debian, it's in Etsy network interfaces. You tell it to, create the interface and then set it up with DHCP in this particular case, and it takes care of all the IP set and IP link commands for you. OpenWRT has a nice GUI to do all this sort of stuff, and can also use the hardware present on most CPE endpoint routers and switches to do it at a hardware level, so you can set one particular port to have a tagged VLAN everywhere else be untagged on that port. So here's sort of what I've done with VLANs in my home network. So I've got my normal router on the edge there, which has three main VLANs: the production network, or untagged, which is production in the sense that it's the Netflix and YouTube that my kids watch, along with my web host, the work computers and desktops for my wife and all of that. Then I have another one, or an actual tagged VLAN for the Wi-Fi guest network. So all the traffic there is segregated out and firewalled off completely from all the other VLANs. And I've also put this, what I've called an access VLAN, or that's probably not the right terminology. It should be, I think, a distribution VLAN, but that's where all the other routers that I'm mucking about with sit, so they can talk to each other. So I've got a OpenSense test network, same with OpenWRT, and the internet for the K-Nori tutorials, which I'll link later. It's a really interesting tutorial on where I learned most of the stuff I'm talking about today. is. Okay, so next one is we talk about routing and what is a router. I think it's a computer that has two or more interfaces, and it does some sort of computation to determine where a packet goes, which interface the packet goes to. In Linux, it's reasonably simple to turn a Linux machine into a router. You add to the sysctl config this set of stanzas, tell it to forward for IPv4 and IPv6, and we're done. Yeah, no, not really. That sets up the ability to do routing, but you also have to do things like actually add routes. So static routes is the normal one, usually manually added or by scripts, including things like scripts from DHCP, which is, as you probably know, a mechanism to dynamically assign IPs within a network. They will also send out information like the default route for the network and DNS, NTP servers, whatever else. There's a whole bunch of stuff you can do with DHCP, which I should probably have talked about, but I didn't think of it. So this one here is just adding a route via a particular router on an interface, WireGuard interface in this case. You can also, do IPv6. And I never did get this to work right, so you can see it all. But this is, a few more. But manually adding these, you can imagine becomes quickly becomes unwieldy with expanding networks. It's like this one. So this is sort of my home network with the Kia Ora side expanded on a little bit. And you can imagine for a machine, say in the in the OpenWRT test network there, to try and talk out to something in the Kia Ora network, it would have to have a lot of static routes to know where to go properly. So this is where dynamic routes come in. So a dynamic routing thing is where you advertise the LANs on your router, discover routes to LANs on other routers. If you need to, do some logic and then add them to the kernel space routing table. On Linux, we don't have this built into the kernel, but we have some user space daemons and talking to the kernel networking stack. So the main protocol is this open shortest path first protocol. It uses the Dijkstra's graph minimization cost, or graph traversal cost minimization algorithm, and is defined in the RFCs 2328 and 5340. And it's for dynamically assigning routes within your network. The other dynamic routing protocol is border gateway protocol. Oops, that didn't work well. But that's for talking outside, sharing your dynamic routes outside your network and as part of an autonomous system. And this is sort of something I don't really know a lot about and is what I would consider even more advanced than slightly. For the user space daemons, the main one I've used is the Berkeley Internet Routing daemon. There's also Quagga OpenBGPD from the OpenBSD project. There's significant overlap, but they are different and support slightly different things. I've not used Quagga. There are probably others. I think there are specific ones within things like the Cisco iOS and MikroTik operating systems, but I'm not at all familiar with them. So the Berkeley Internet Routing daemon, or BIRD, is a very powerful and complex to configure, although it's not quite Turing complete. I would recommend you use version control on, I use git on /etc/bird, wherever your distro stores it. That's what I reckon, because then you've got tracking changes which can undo your last change, which made nothing work. So the bird config file is built up of these protocol blocks, and the most important part, I suppose, is the router ID. That's usually one of the router's IPv4 addresses, and the default that Bird chooses the lowest one that's not on the loopback interface. It needs to be unique across your network, not necessarily globally. There are lots of protocol block types, including OSPF, BGP, there's RIP, a whole bunch of them. The documentation for Bird is really good and tells you a lot about what each of these blocks needs. It's relatively straightforward to follow. So the protocol blocks are how Bird knows who or what to talk to and how. So in the next slide, we've got an OSPF protocol block, which has an area and an interface. Oh, that's right, I was going to mention, so back here we've got this device protocol. So in there you can specify to ignore particular network interfaces or give certain others higher priority or higher cost, that sort of thing. That's all good. So this is a bit of a more advanced diagram with a reasonably complex set of things, but it shows you so each circle there is a protocol. There's the OSPF you can see at the top, and then the kernel. So, it's importing routes from the wider OSPF protocol that it gets, stuffing it all into the master table, and then exporting that to the Linux kernel. Now, on the other side, you've got some strange BGP-ness, which goes into this temporary table TR10, then through a pipe. And pipes are where the logic can happen. So you can start aggregating or ignoring or doing things as needed to the routes that are discovered. You can put them in between any other protocol and any other table. All right, so what inspired me to do this talk is this funky thing I found you can do with OSPF. So say you have some necessary service within your network that can be where the data is more efficiently obtained across local links, but can still get the same data across a more expensive link if the local version goes down. So all you need is an IP on a host or many hosts that provide that service, and you can use that same IP in two different places in the network. One might think that this is going to lead to confused routes, but OSPF helps us out. So there's a little bit of a diagram of two offices, one in Perth and one in Hobart. Both having computers on the bottom talking to their own network with a router in the middle and an expensive link connecting the two. But then we have these two services running on this 172.17.055 IP address. And the way OSPF works is you can add a cost. It's just a number to scale within OSPF. You can add a cost to each link on a router. So on the Hobart office router, you'd say the link up to that top network is say 10, and then the expensive link off to Perth is 100. And what will happen then is that Hobart router will think the 172.17.0 network is local, and everything on that side of the link will then talk to that service on that side. If the local link goes down, we'll then go across the expensive link to Perth, and hopefully with your synchronization, the data's the same, and it all still hangs together. So that's right. This was what was causing. So late last year, there was a big outage with Facebook. This is what they were doing with their DNS services, and they added a line in which turned off the part of the way OSPF works, turned it off, so no one could talk to the DNS, which meant nothing worked. So you do have to be careful with these things, but they're pretty powerful. All right, so I sort of thought, why would you want to use a real router? And the main reason is probably going to be performance and scaling. On a Linux-based router, you have a packet come in through the NIC hardware, which then has to copy the whole thing to driver memory, then off again to various kernel subsystems, which can make the routing decision, or potentially going out to some user space application if needed, and then back out the same path through the kernel subsystems into the driver memory and then out the NIC hardware. In comparison, a enterprise level router has the packet come in, and just enough of the packet to get the address is copied to the routing silicon, where the routing decision is made, and then the silicon is switched to forward the packet out the correct NIC hardware at wire speed. So it's a switched physical connection usually, although I'm sure that's all done in ASICs and FPGAs these days. So performance, I mentioned that. So there's a lot of work being done currently on Linux with zero copy networking. So we can do sort of the same sorts of things, pass pointers around, I suppose. I'm not sure how it all goes together. And then the IO ring part of Linux also has some smarts and other bits and pieces that tie into this pretty well. Some other considerations. So network engineers are generally not familiar with Linux networking. They're much more familiar with things like Cisco IS or iOS, and MikroTik's operating system, excuse me. They have much more significant skills in those networking stacks than they will with Linux. There's also the availability of hardware for, in terms of ruggedness and suitability for working in a data center. A lot of stuff that Linux supports is not great at that, and power consumption is another problem. Not so much in the data center, though it's becoming more and more important, I suppose. But you can also sort of have both. So OpenWRT is my favorite thing for doing networking with. It does work on a lot of enterprise level routers and switches and stuff, and does support a lot of the hardware on a lot of those. So yeah, I didn't get to explore BGP as much as I'd like. I'm not too confident in my understanding of it as yet, but it is how the internet's put together, and can do some even more funky tricks, like our service example. Things like the Netflix data centers and Netflix caches. You can do all sorts of fun tricks. All right, so I put in some bonus homework. If you want to learn a bit more, you can try asking yourself those few questions there. I very highly recommend going through Kay Norrie's OSPF and BGP tutorial. It's really worthwhile. I didn't cover OSPF areas much, and so the idea is that OSPF is done in areas, and you can split that up within birds, so it talks areas. So you usually have the area 0, which is where all routes are shared, and you can then fractalize that out to other areas with smaller networks. And then there's also the problem of authentication and authorization. So OSPF by default will just accept routes from anywhere. You may want to hash that or password protect it or other things, all certainly possible. And the stuff I have done with BGP was a bit minimal and requires internal BGP to be set up sort of manually. I'm assuming there'll be a automatic transfer of internal aggregate networks, but I haven't looked into it all that much. So the resources for this, these slides, the Bird website's great, so is OpenWRT. The IRC channel for OpenWRT has been really helpful to me over the last couple of years. And if you want to know more about why Facebook was down for 5 hours, there's a really good YouTube video from Ben Eater to look at. And there's the 802.1q link, which I couldn't get to work in the other slide, I think. But yeah, that's the protocol design documents there. And that's my talk. I'm a little bit early, I think, so feel free to ask some questions.
Yeah, we don't have any questions yet. Now we are on a delay, so if you've got any questions, please type them in really fast. Yeah, so we're talking about 30 seconds in the future. So we'll give it a couple of, give it a few seconds, and then that might be it. There is some discussion in the chat room, people talking about general networking stuff and that, and recommending their favorite little things and crazy stuff. So
excellent.
Yeah. So we've got a networking theme at least. Okay. I think we don't have any questions. All right. Okay. So yeah. Sorry, my brain's gone. So yeah, thank you very much, Paul.
All right.
Obviously a bit stressful week moving for you, but thanks for joining us and giving us a talk.
No trouble at all. Thank you.
Bye.